We are going to look at gas laws today. We'll go through pressure and gas laws. We'll do some demos tomorrow. I'll have some liquid nitrogen tomorrow that we can look at some of the gas laws and some other stuff. So we will, whoops. So some substances that exist as gas. There's only 11 elements that are gases under normal atmospheric pressures. If you change pressure or temperature, then you may have some other substances become gases, but the diatomic gases are the nitrogen, oxygen, chlorine, and hydrogen. Monatomic gases include all the noble gases. And then there are some compounds like propane and methane. Those are all gases, too, can be gases. Table 5.1 has more of those compounds. That's just a reference for you. Okay, the pressure of a gas, it's measured by taking the force per area. So it's like you have this column of air that's pressing down on you, and the force over the area that you're looking at is its pressure. The SI unit is a Pascal. We will actually be using ATM and millimeters mercury a lot more. ATM is just atmospheres. That's what it's called. The atmosphere is much denser near the Earth's surface because of the gravitational pull. Also, if you think about if you are in Death Valley versus on top of Mount Everest, in which spot do you have more atmosphere on top of you pressing down on you? Death Valley, right? You have Death Valley is below sea level. You have a lot more atmosphere above you. So the pressure is higher the closer to the Earth's surface you are, or to the Earth center of the Earth. The atmospheric pressure is exerted in all directions because gas is a fluid. It can move, flow, so it's a fluid. Gas is measured with a barometer. This is a picture of a barometer. So you have this long tube, long capillary tube that's closed on this end. This end's closed, and this is actually a vacuum inside, so you have no pressure acting on it. This well is open and is filled with mercury. It's open to the atmosphere, so the atmospheric pressure is always pushing down on this mercury. As you get more and more atmospheric pressure, it pushes down on this mercury. The only place that mercury can go is up the capillary tube. So the higher it gets, the higher the pressure. And how we measure the pressure is the distance from the mercury in the well to the distance of the mercury at the top of the capillary tube. And that is the measurement in millimeters mercury, inches mercury, it could be centimeters mercury, whatever. A lot of times you'll see millimeters mercury. So standard atmospheric pressure. This is part of when we see in a problem we'll have, it's called STP. That is standard temperature and pressure. So the standard pressure part is these values where it's 1 atm or 760 torr, or millimeters mercury, or 760 torr. Torr is a unit that's been named after some guy who studied gases. We won't use that one very often. Just know that. Millimeters mercury. I don't know. 101,325 pascals. I'm sure Pascal is the name of some guy who studied gases. What? No, it's the Greek god. Greek or Roman. I don't remember. Mercury's Roman. So, what? True. True. Named after a god. So these are all equal to each other. We can use them as conversion factors. We can use them as equivalents. So 1 atm is equal to 760 millimeters mercury, equal to all those others. So if we have, look at the last one, a Pascal. If we had kilopascals, how many kilopascals would that be? 101.325. Yep. Move the decimal 3 spots, and you'd have kilopascals. Okay, so let's do a conversion here. If the pressure outside of a jet plane flying at high altitude falls considerably below standard atmospheric pressure, so the air inside the cabin must be pressurized to protect the passengers. What is the pressure in atmospheres if the barometer reading is 688 millimeters mercury? So if we have 688 millimeters mercury, how would we get that into ATM or atmospheres? Units need to be millimeters mercury on the bottom, right? And we'd have ATM on top. So 760 on the bottom and 1 on top. Yep, you just use your equivalents that we just had. So it's going to be less than 1. We're going to divide. And what do we get? Point something. 0.905. And our units are ATM. There we go. Questions on using those? Okay, so the pressure can also be measured by a manometer. A manometer measures anything outside of atmospheric pressure. So if you just want to know the pressure of a gas, you have this gas in a container or a flask. It'd be connected to this U-tube, and this U-tube is filled with mercury. Without a gas in here, if it's all a vacuum, the level of the mercury would be equal to each other. Okay, but with this gas in here, and it exerts a pressure, the only place for this gas to go is out of this tube and push down on the mercury. And once the pressure from this mercury down is equal to the gas pushing down, it would stabilize, and the distance between this height and this height would be your measurement in millimeters mercury, which would give you your pressure. Okay, the gas laws are simple mathematical relationships between volume, temperature, pressure, and quantity of gas. So we will look at Boyle's law, Charles' law, and Gay-Lussac's law today. So in each of these laws, you have varying, like the volume may change, or the temperature may change, or the pressure may change. But one of those variables is always held constant. So we only have two variables changing. So in Boyle's law, we're looking at changing pressure and volume, and the temperature remain constant. And if you think about pressure and volume, so let's say you have a syringe that's closed on the end, okay, because I can't think of another example. So you have a syringe, you open it up, or pull the plunger out, and then you cover the end. Now if I decrease the volume by pushing the plunger in, what happens to the pressure inside? The pressure goes up, right? You're making those molecules get closer together, you're building up the pressure, so as the volume goes down, pressure goes up, right? Eventually, yes. Or if our volume went up, the pressure would go down, right? They're inversely proportional. So we can write this little equation where K is this gas constant, and that would stay constant for whatever gas. As long as you don't change gases, you're going to keep that same constant, which is why if we change the conditions, so we haven't changed the gas, we haven't changed the amount of gas or the temperature, we can change these conditions. K is going to stay the same. So we have the pressure and volume of the first initial condition is equal to the pressure and volume of the second. We can solve for whatever the unknown is then. So here's a picture where if this is our initial conditions in the middle, If we decrease the volume, it's going to increase the pressure of that gas. If we increase the volume, it decreases the pressure of the gas. It's inversely proportional. Let's do an example. A sample of oxygen gas has a volume of 150 milliliters. When its pressure is 0.947 atm? What's the volume of the gas at a pressure of 0.987 atm if the temperature remains constant? So what's our initial pressure? 0.947. Now it does not matter what units you're using in this case, as long as they're the same on both sides. What's our initial volume? And that's equal to, what's our change pressure? And do we know the second volume? No, that's what we're going to look for. So if you look here, our ATMs are canceling out. That's why as long as they are the same on both sides, fine. So what is V2? Right, milliliters. Whatever our units were here, that's what we're left with. So we have milliliters. Did everyone get that answer? Okay. So how about this helium-filled balloon? Contains 125 milliliters of gas at a pressure of 0.974. What's our initial pressure? Initial volume? Okay, what's our change pressure? We're STP, so standard temperature and pressure. What would be standard pressure? One, what? ATM, right. You could have, well, we want to use ATM because this number is an ATM. If that number would have been in millimeters mercury, you could use millimeters mercury. So we'd have 1 ATM times V2. So ATMs cancel, and V2 would equal 120 milliliters, correct? There we go. Questions on Boyle's law? Okay, Charles's law is the volume-temperature relationship. Okay, so when pressure is constant, gases expand when heated, or they collapse when cooled. So if you think about think about balloon. Say you have a balloon, one hot summer day, you're out at a carnival, and you win a balloon, okay? And you decide to go into the house, and so you go in the house, and it's really cool and air-conditioned. What would happen to that balloon? It shrinks a little bit, right? The volume decreases. So as the temperature, you went inside a cool room, temperature went down, right? So what happened to the volume? It went down also. So they are very directly.
So you're saying don't buy a full balloon inside an air conditioning when it's really hot out because it will go out like hot and waste money.
Balloons can usually expand a little bit. Yes. Yes. If you got something in the cold and it was completely filled to its limit, and then you try to take it outside somewhere where it's hot, it'll. Oh, and the
Yeah, that's
Don't even
different.
like when you let it heat up, it like
That's way different.
expands.
the bottle or the water? What are you talking about? Because in that case, it's because the water is expanding. Because water expands when it freezes.
It's the opposite. It's not really a gas. Water is.
Okay,
It's a
then
compound.
what about pop? When you put pop in the freezer, it's what? That?
Yeah, different compound. Pop has water in it. Water expands.
Yeah.
And freezes.
It's because the liquid's trying to expand, and the set volume of the aluminum can can't hold it. It gets so much pressure that it explodes. Trying to think, what could be another example?
Liquid. That has
No,
water.
not liquid, gases. We're looking at gases.
Alright. Liquid oxygen.
Have an old car in the summertime and fill the tires up and get out inside.
Yeah. But that would be a good pressure, because usually you take the pressure of it.
Not unless you need to run on the tire.
Yeah.
Evaporation.
Yeah. Okay, so we saw that they are directly related. We do have to, since the gases expand at the same rate, and their energy relates to Kelvin, not Celsius, we're going to have to change everything to Kelvin. Do you guys remember how to change Celsius to Kelvin?
You do some formula.
273, yes. So you take the Celsius temperature and just add 273 to it. Nope. Kelvin to Celsius, you'd subtract it. Because zero, if you think about 0 Kelvin's absolute zero. You aren't going to add 273 to that to make it 273 Celsius. You're going to subtract 273 to make it really cold. Whoops. So we'll have V1 over T1 is equal to V2 over T2 for our equation, since they are inversely directly related. Okay. So let's do, well, here's a picture of it, I guess. Here, if we have this here, we have higher temperature, the volume will increase, versus lower temperature, volume will decrease. It's also related to pressure, but we have a separate law for that. Tomorrow we'll combine all these laws together to get one nice combined law. So the capillary tubing is another way they can measure this. They can measure how high this mercury rises by heating this gas. It expands. Okay, so a sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume will the gas occupy at 50 degrees Celsius? What's our initial volume? 752. And that's going to be over what? Right, we have to change it to Kelvin. So 298. And we're looking for our new volume, so V2, over what's our temperature? 273. Right. So V2 is, you can cross multiply, divide. You could divide these two numbers first and then multiply across. However you want to solve that, you'll get the same answer. But your answer would be what? It's heating up, so the volume should get greater. 800 what? 15.08, so I'm going to just say 0.1. And what's our units? milliliters. Good. And the next one, a balloon filled with oxygen gas occupies a volume of 5.5 liters at 25 degrees Celsius. What volume will it occupy at 100 degrees Celsius? So what's our first volume? Right, and I can use 5.5 liters. It doesn't matter what our volume units are, as long as they're the same on both sides. 25 we already know is 298 Kelvin. We're looking for our second volume, and what's our new temperature? 73. So V2 is equal to what? 6.9 liters. Very good. Questions on Charles' law? It just happened. Hold on. Okay, Gay-Lussac's law is looking at pressure-temperature relationships. So, you guys' example of tire pressure. So in the summer, you have normal tire pressure. As it gets colder out during the fall and winter, what happens to that tire pressure? It goes down. Your tires get flat in the winter, right? Or your bike tires, if you go out right now to look at your bike tires, they'd all be a little flat because the pressure has gone down because the temperature goes down. Or another example, if you had a water bottle and you drank it all, but you left it in the car, and it gets really cold out that night, and you go in the morning and look at it, what's it going to be like? Some of those flimsy water bottles that we have now, like it's being crushed in a little bit. So the temperature has gone down inside the water bottle, and so the pressure has gone down inside the water bottle. Now the atmospheric pressure outside of the water bottle is higher, so it's pushing in more on the water bottle, and it makes it collapse a little bit. As soon as you open it, you've made the pressures inside and outside equal, and pops back out. Okay. Now you can explain that to your parents the next time you get a crushed water bottle in your car. There you go. So we're going to use this example or equation, P1 over T1 equals P2 over T2, since they're directly related. And let's do this example. So here's another example. The gas in an aerosol can is at a pressure of 3 atm at 25 degrees Celsius. Now this one is about warming it up. When you are using an aerosol can and the gas is escaping, I know we're changing the amount of gas, but the atmosphere or the pressure inside the can is also going down. What happens to that can? What does that can feel like as you're using it usually? Have you ever noticed? Like if you sit there and spray it for a while, usually it will get a lot colder. The can gets colder because the pressure is going down, temperature will go down inside. An aerosol can, if you sit there and spray it for a long time, then it will go down. So in this case, we're going to warm it up. So the directions on the can, warn the user not to keep the can in a place where the temperature exceeds 52 degrees Celsius. What would the gas pressure on the can be at 52 degrees Celsius? If we have P1 over T1, our initial pressure is 3 atm. What's our initial temperature? Initial temperature. Yep. And that is equal to, we're looking for our new pressure, 52 degrees Celsius is how many Kelvin? 225? 325. Okay, so what's our new pressure? Hold on. It disconnected. Okay, so what'd you get for P2? 3.27? ATM. Okay, so at this pressure, the can must not be able to withhold this pressure or withstand this pressure, so it's going to explode. Yep. No one's ever done that before, right?
What?
Throwing aerosol cans into the fire.
No, what are you talking about? I have done that actually.
What?
That's really bad.
Yeah.
You know what can be? We took, only it was a AAA battery. We threw it in and it just started exploding.
Yeah, it would.
It's not his battery.
Just don't put styrofoam or plastic in the fire. That's bad. It does.
We do that all the time.
So bad. So bad.
And the last one. Temperature within an automobile tire at the beginning of a long trip. It's probably supposed to say not log trip. A long trip is 25 degrees Celsius. At the conclusion of the trip, the tire has a pressure of 1.8 atm. What's the final Celsius temperature within the tire if the original pressure was 1.75 atm? So what's our initial P1? And what's our initial temperature? And initial or second volume or pressure? And we're looking for T2, right? $306.5. Okay, is that the answer to the question? Ah, yes, because it wants Celsius. If it wouldn't specify whether it wants Celsius or not, you could leave it in Kelvin. That'd be fine. But they want Celsius, so how would you get that into Celsius? Subtract 275, and you get 273, I mean, yep. There you go. Questions on Gay-Lussac's law? Okay, tomorrow we'll combine these together and then do a couple little demo things.